All right, find the point on the line y equals 2x plus 5 that is closest to the point 3, 4. All right, so y equals 2x plus 5. Let's just play with this on Desmos for a moment. I'm going to reload it so that we get a normal axes. Let's see, we had y equals 2x plus 5. And we want the point that's closest to, what was it, 3, 4. All right, so if we just look at this on Desmos, you can kind of tell that the point that's going to be closest to 3, 4, it's going to be the one that's right sort of here-ish somewhere. It's going to be the one where if you drew a straight line from the point to the line, it would meet it in a right angle. But we can use calculus to figure out the exact coordinates of that point. So let's do that. I'm gonna draw that graph. 2x plus 5 looks like this. And the point 3, 4 is over here. And here's what I want to do. I'm going to draw a point on here. And I'm going to call that point x. And since it's on this line, its y-coordinate's 2x plus 5. And the thing that I want to minimize is the length between these 2 points here. I want to minimize the distance between those 2 points. Now, we can use the distance formula for that. The distance is going to be, remember, distance formula tells you the square root of the difference in x values plus the difference in y values. And let's see. So let's just go through and work this out. X minus 3 squared. And then this other one, it's going to be 2x plus 1 squared. Now I'm going to square all this out underneath the radical. Remember, you can't just let those the square root and the square cancel out because we've got stuff added together. We've got to FOIL both of these out and go from there. So x minus 3 squared gives me x squared minus 6x plus 9. And then this gives me 4x squared plus 4x plus 1. So the distance between these 2 points is going to be the square root of 5x squared minus 2x plus 10. All right, now I could go plow through here and take the derivative of this and set it equal to 0. There's nothing wrong with that, but there's an easier way to do this. We want to minimize this length. Instead of minimizing the length here of this purple line, I could draw a square. And let me just say what's going on here. This is a movable point. We can move it along the line, and we want to move it until the length of that purple line is smallest. Well, if the length of the purple line is smallest, so is the length, or I'm sorry, the area of this square. So instead of minimizing this, let's minimize, I'm going to call it S, which is d squared. S then is going to be 5x squared minus 2x plus 10. That's going to be a whole lot easier to minimize because we don't have that square root on there. And it's going to give us the same value of x. So if I take the derivative of this, S prime is going to be 10x minus 2 And if I set that equal to 0 and solve, I get x is, let's see, 10x is 2, so x is 2 over 10, or 1/5. So x is 1/5, and y is going to be, we can get y by just plugging back into here. 2 times a fifth plus 5. So what is that? Let's see, 5 and 2/5. So let's see, 5 and 2/5. That's 5 times 5 is 25, 26, 27 over 2. Or 5.4 and 0.2 if we write it as decimals. So that's the point that's going to be closest. And if we come back over here on Desmos and look at it, I'm going to put the point in here. 0.2, comma 5.4. That point is on the line, and if we were to draw the line connecting these 2 points, it would meet this other one in a 90-degree angle. So that is the point that's closest to 3,4 on that curve. All right, let's see this next one. I think this next one's the last example. Yeah, let's look at this. Okay, we need to design a box with a square base and an open top and a volume of 32,000 cubic centimeters. Find the dimensions of the box that will minimize the amount of material used. So this is kind of like that first box problem, only in this case, instead of being specified that it has to be made using this amount of material, and we maximize the volume, in this case, we're given a volume we have to meet, and we're trying to use the minimum amount of material possible. And so, let's see. Let's draw our box then. Box is going to look like this. It's a square. And it has no top. So it looks like that. Let's call this x. Let's call this y. Now what they tell us here is the volume has to be 32,000 cubic centimeters. So x squared y, that's the volume. And they want us to minimize the amount of material used. That's going to be like the surface area. If you look at this box, it's got 5 parts to it. It's got the sides here. Each of these sides is x by y, and there's 4 of them. So this is 4xy. And then it's also got the bottom. And the bottom, which you can only see part of here, but the bottom is a square that's x by x. So that's the function that we're trying to minimize there, is 4xy plus x squared. So first up, let's get rid of this y so that it's only a function of one variable. So we'll do that by taking this, and if you solve that for y, you get y is 32,000 over x squared. So our area is 4x times 32,000 over x squared and plus x squared. So let's see, 4 times 32 is 128. So you get 128,000 over x plus x squared. A prime then is going to be, let's see, this is going to be minus 128,000 over x squared plus 2x. And we want to set that equal to 0 and solve. All right, I'm going to move the 128,000 over x squared to the other side. So you get 2x is 128,000 over x squared. Let's see, if you cross, well, you get x cubed over here, and then 128,000 over 2 is 64,000. So take the cube root of that. Oh yeah, that works out nicely, because the cube root of 64 is 4, and the cube root of 1,000 is 10. So cube root of 64,000 is 40. All right, so we get x equals 40. That's our critical number. We need to make sure that that's actually a, what are we trying to find here? Is this a minimum? Well, I'm going to check that by looking at Desmos. Let's see, what is it we're trying to look at? The function was our a 128,000 over x. Let's call this a equals plus x squared. Now, unsurprisingly, we don't really see anything when we look at this. We have to back way out before we see anything. Honestly, maybe this isn't the best way to do it. Let's go back and check it just using calculus. So is 40 a minimum? Well, let's pick some numbers on both sides. Let's see. Let's pick 1 and let's pick 100. So if I do a prime of 1, where's my a prime? Here it is. A prime of 1, I wind up with, let's see, negative 128,000 and then minus 2. So that's definitely negative. If I do a prime of 100, that's a negative 128,000 over 100 squared plus 200. Let's see, what is 100 squared? It's 10,000. This is one I was thinking I'd be able to just plug it in and see the answer immediately. But let's see, negative 128,000 divided by 100 squared equals 12.8. So this is minus 12.8 plus 200. So that's definitely a positive number. So sure enough, the function goes down, then goes up. And so we do have a minimum there. So x equals 40 gives us a minimum. Let's go back to what was the question asking. Find the dimensions of the box that will minimize the amount of material used. So x is going to be 40. What about y? Let's see, y is 32,000 over 40 squared. 32,000 divided by 40, divided by 40 again is 20. So those are the dimensions that will minimize the box. Or rather, I should say, will minimize the material needed to build the box. All right, that's it.